So, in the last lecture I discussed about you ductile iron or nodular iron. Now, I am going to discuss with you malleable iron or sometime known as vermicellar iron, vermicellar. Okay. So, what is it? Malleable iron is a solid state product. First of all, let me tell you, grey iron, spherical graphite iron, all of them or white iron are produced from the liquid, but this is solid state product. In this case, the graphite forms like a, it is like a deformed graphite. It is not a deformed graphite, irregular separate graphite. You can see here forms, and they are called tempered graphite. Basically, tempered is a better term, tempered graphite. So, these things are very non-uniform in shape, neither they are spherical nor they are nodule, nor they are flaky, they are not, but fact that they form graphite and they are uniformly dispersed, and you can have a matrix ferrite, perlite or tempered martensite. Ferrite casting requires, well, obviously these are done by annealing, and which you will discuss in detail now. So, ferrite requires 2-stage annealing process, perlite requires first stage annealing or 1-stage annealing process. So, let us first discuss what it is possible to have a composition that would form a grey cast iron on extremely slow cooling condition, but form a white cast iron on regular cooling, that we have seen. That means, if I take a steel alloy composition of cast iron and cool it very fast, it is instead of forming graphite, it will form cementite, that we have seen. Basically, there are two competitive eutectic reactions. One is liquid going to gamma plus graphite taking place at 54 degree Celsius temperature. Other one is liquid going to gamma plus cementite, and it occurs at 1146 degree Celsius temperature. So, hardly about 8 degree difference, 1146, 1154. So, if you cool it very slowly, the first reaction will happen and you will form graphite instead of forming cementite. So, but if you cool it fast, the second reaction, the liquid going to gamma plus cementite will happen, and in that case you will form the white cast iron. As I told you, white cast iron is a very brittle material, it has large chunk of cementite present, and because of that is brittle, correct. And let me again show you these pictures, otherwise it will not be clear to you. So, white iron, white iron has large cementite and a matrix of gamma plus cementite, which is where the gamma again transformed to perlite in solid state. So, this is the very brittle. Again, in a hypoeutectic also you have large chunks of cementite, both the cases. As you know, cementite is not a low metastable phase. This is not metastable phase, so it is not the lowest energy configuration phase. It will, if you provide some diving pores, it will transform into graphite, and that is what is, this is what is used for the formation of your malleable iron. So, what we do to do that, we reheat this white iron and at a high temperature. High temperature means at about 850 degree Celsius temperature, and this will lead to decomposition of cementite. Why? Because Fe3C, if you see here, if you heat, it will transform to 3Fe plus carbon in form of graphite, correct. That is what will happen, and this is exactly the way malleable iron are made. So, in malleable iron, you take the white iron, heat it up to 850 degree Celsius temperature, keep it long 48 hours to 72 hours, sometime 96 hours, so that this transformation happens. Fe3C, which is present in metastable phase, it gets converted into Fe plus graphite. Now, at 850 degree Celsius temperature, this Fe will be gamma iron, and then if you cool it down, this Fe will be converted into either perlite or ferrite, correct, depending on the carbon concentration. So, graphite formed by this process, this is a solid state process, right. We are not cooling it from liquid, we are taking the white iron, heating it up to 850 degree Celsius temperature. So, this is a solid state process. The graphite formed by this process is quite different from the eutectic graphite, because eutectic graphite, which forms by this eutectic reaction, liquid going to gamma plus graphite, forms in liquid state, liquid to solid transformation, but this graphite in the malleable iron forms by solid state reaction. So, therefore, this is not a spherical separate graphite, it has a irregular shape. forms. That is what you have seen in the last picture, irregular surface picture. Now, depending on the depending on your cooling conditions, you can also either have a ferritic matrix or you can have a Paletic matrix. One can also create martensitic matrix, that I will discuss maybe end of this lecture. I have been telling you the formation of martensitic matrix, but I have never discussed with you. I will tell you that also. So, you have basically these what's called graphite, which are actually called tempered graphite or solid state formed graphite, and then a surrounding is a ferritic matrix. As you see a higher dimension picture of graphite, you see irregular separate graphite picture, correct, here also. So, because of these tempered graphite, malleable iron is very malleable. Malleable means what? Very ductile. Normally, malleable iron is not used in the automobile industry, it is normally used in the space industry, because space requires certain applications where the graphite, the ductility is a major issue, and graphite also needs to be of this kind of shapes. Now, although graphite is irregular shape, but it has very sharp edges also. So, therefore, the problem of the stress concentration remains in this case. You can also create Paletic matrix here. How? You can actually see the way we can create matrix is basically depending on the heat treatment schedule. As I told you now that how this form, I take a white iron of same composition like a grey iron, 3.5 to about 4% carbon, silicon is about 1% or 2.5%, cool it very fast, you form a white iron. Now, you annihilate at 850 Celsius temperature. If you annihilate for shorter time, let us say about 24 to 48 hours, that is the shorter time. Okay, 24 48 hours is also short time. If you annihilate that time, then what will happen? This graphite, the transformation of this cementite will happen. Cementite will transform to Fe plus graphite. Transformation will happen and graphite will nucleate, and the graphite will grow. As I told you, the graphite growth requires more carbon. So, it will absorb the carbon, from the nearby matrix. So, if I nucleate this graphite from the cementite, so for it grows, it will take the carbon from the nearby region, the solid state, and become bigger. Once it become bigger, nearby regions will be depleted of carbon, and this depletion of carbon will if it is happening uniformly all throughout it, all the nodules becomes big and then whole region become depleted of carbon, then it will form ferritic matrix, because there will be no carbon left, or virtually very little carbon will left in the matrix for it to have a Paletic transformation at 723 degrees Celsius temperature. So, that happens if when you annihilate for longer time, when you annihilate for 72 to 96 hours, but if you annihilate for shorter time, 24 to 48 hours, the diffusion of carbon will not be happening uniformly. Only the regions which are nearby these graphite nodules or graphite non nodules, graphite tempered graphite things will be depleted of carbon and they will become ferritics. So, then you can create Paletic matrix. On the other hand, if you keep it long time, 72 46 96 hours, then the carbon will diffuse to graphite from all the regions and the whole matrix will become depleted of carbon, and then it forms ferritic matrix, correct. So, that is the way it forms. So, in ferritic matrix requires two stage annealing, that is why. What is two stage annealing? First you anneal at 850 degrees Celsius temperature to form the graphite, then you cool it down. From the graphite will become critical size and grow. Then you keep reduce the temperature. This happens for about 48 hours. This heat treatment. Then you reduce the temperature to about then you increase the temperature to about 950 degrees Celsius temperature. At the temperature, all the carbon will diffuse from different parts of the sample to the graphite, and then this will be the matrix will be depleted of carbon. It will form ferrite. But if you want a Paletic matrix, the 850 degree annealing is sufficient for 48 hours. Okay. So, that is how we can create different kinds of the graphitic morphology in cast iron. Now, in next 5 to 10 minutes, what I am going to do is, I am going to discuss with you the in one slide how things happens. As you know, this is the iron carbon phase diagram, this is the commercial range. I am just showing you temperature versus composition. This is the commercial range of the for the cast iron family, as you see here. So, most of the alloy composition will vary from 2.5 to 4.3% or 4.25% carbon, and this is the Fe3C point, 6.67% carbon, 6.67. So, this is 0.8, this is 0.02, this is 2.01 or 2.1 rather, okay, and this is 2.5, this is 4.26% carbon. So, this is the commercial range of the cast iron, correct. Now, what are the different things? If you cool fast cool will lead to perlite plus cementite, as you see here. These white things are cementite and these are perlite. So, that is the way you form the white iron, correct. Moderately cooled and you have quite a lot of silicon. Second thing, you have to have silicon and moderate cooling, then you have perlite plus graphite flex, correct. You see here flex or graphite, and if you cool it slowly, silicon is present, then you can have ferritic cast iron. So, difference between this perlitic grey iron and the ferritic grey iron is that your cooling rate changes. If you moderately cooled, moderate means how much? About 10 to 15 degrees per minute, and slow cool means 1 degree per minute. So, if you moderately cool, you form the perlitic grey cast iron, and if you cool it very slowly, you form the ferritic cast iron. That is very simple. If you cool it slowly, graphite will have more time to absorb carbon from the nearby regions, and nearby regions will be depleted of carbon, then it will form ferritic matrix. Now, this is one part of the story. Second part of the story is what? You can modify the shapes of this graphite, correct. That is done in liquid state, whole thing I am talking in liquid state. So, what you do is that you can add magnesium or cerium or calcium or mixed metal. So, what you can do, you can form graphite nodule. The GN is basically terms of the graphite nodule. If you slowly, moderately cool, if you form graphite nodules and the perlitic matrix, but if you cool it slowly, you will form the ferritic matrix, same as earlier. Why? Graphite will absorb all the carbon, but basically you are adding this magnesium or cerium, then only you can change the shape from flex to the nodular. That is the idea. Without that, you cannot basically do that. So, the addition of magnesium, cerium, lanthanum or calcium is basically due to what? Due to the shape change. So, thus this is what is for the solid state, liquid to solid state, from the liquid where the eutectic reaction happens. Now, there is another part of the story. If I take this white iron which contains lot of cementite and perlite, and I reheat about 700 degrees Celsius temperature, 700 is wrong, I would tell you it is 850 degrees Celsius temperature, okay. So, 700 is wrong, not correct, sorry, and I keep it 24 to 48 hours, that is why 30 plus hours, and if I cool it, if I keep it long time and cool it slowly, I form ferritic matrix, if I cool it fast, I form perlitic matrix. That is one part. Second part is that you form this perlite or ferrite depends on what is your what is the way you are treating, at what temperature you are treating. If you treat at high temperatures for long time, that is about say 48 to 96 hours, you form the ferritic matrix. If you treat it slowly, these things at a low temperature, sorry, not at lower time about 24 to 48 hours, then you can form perlitic matrix. So, this is in a nutshell adapted from the book of Callister, and you can see the figure number 11.5, you can read also. This will tell you the whole cast iron family is together, thus how the different cast iron basically forms. Okay, so, now the things which I am supposed to tell you is that other than this perlite and ferritic matrix, we can also form what is known as your martensitic matrix. That is not difficult. What you do is that for martensitic matrix, because many applications requires grey iron or spherical graphite iron with the martensitic matrix. What you do is that you cool very fast, which is not shown here, moderate and slow cooling both for the grey iron and the spherical graphite and so on. But if you cool it very fast, if you quench in water, after this eutectic reaction, this gamma iron will convert into martensites. Normally, we do not need martensites in the cast iron. Why? Because cast iron are basically ductile, they are very ductile. So, that is why you do not want to create a martensite to make it brittle, that is the idea. So, martensitic matrix is normally not used, but there are few situations where you need martensites, you need a higher wear resistance, at the same time you need the lubrication properties of graphite. So, there actually you can cool it very fast, like quenching in water or oil, you can form these martensites. That is one part. You can also form bainite in the matrix, and that is actually more widely used. Austempered ductile irons, which are very widely used now for the making the connecting rods of the automobile engines, here the matrix is bainite. How do you form the bainite? Again the same way, by isothermal holding at a 350 per 1 Celsius temperature. So, you have the eutectic reactions leading to formation of these flaky or the nodular graphite iron graphites, and then you can actually do this, cool it very fast, go to 350 or 400 Celsius temperature, keep it there for a long time, form the bainite. So, by forming the bainite you can actually use more ductility into it and also strength, because bainite has both the strength and ductility quite a good. So, you can see that it gives you wide opportunities to create different kind of microstructure. From the same alloy I can change the microstructure differently by different mechanisms and create different kinds of properties. I can change the nodules, shape of graphite, that is one part, from the flakes to nodules to tempered graphite in malleable iron, that is one part of the story. Second part of the story is that I can change the matrix. So, it gives you empty number of choices of creating different microstructure. That is the beautiful part of these cast irons, and that is why we wanted to spend a lot of time on that. So, the basic idea is that now if you want to again change the matrix, you can add alloying elements. That is why what is called as alloyed cast irons. You can add chromium, you can add tungsten, you can add titanium, you can add other alloying elements, nickel, to change the matrix, because these alloying elements will change the matrix compositions. This alloy will also change the graphite morphology, that is possible. So, that is the another set of things which we need to discuss, which we will do in the next class. But for your understanding of the cast iron family, this is the basis of the cast iron things which I wanted to give you in one slide, and this is nicely done in Callister book. If you want to look at it, it is available on the net. So, please do read it and try to understand it very nicely, so that you can have a good sense of what is a cast iron family is and what are the different ways you can modify the microstructure, and that is what is the key of from this course which you will get. I can say I am only giving you the tip of the iceberg, because there are many interesting things available in the textbook. That is why you need to follow the textbook. As the exams will be held just about 1.5 months time, is 24th and 30th is the deadline for the last exam. So, and these are the parts which are very important. You should concentrate on these parts more or nicely than whatever I am going to teach for the next subsequent lectures. So, what I am going to do is the next subsequent lecture is that first I will finish off in the next lecture I will finish off this alloyed cast iron. Then I should go into some of these phase diagrams of ceramic systems, which I have not discussed, and this will take me about 3-4 lectures, and after that I am going to start the area of your ternary phase diagrams. That is basically the whole things which plan of discussion. For the ternary phase diagrams will take you about 20 lectures, and finally we will discuss about again come back stainless steels and some other interesting alloy systems where ternary elements are present. Okay. So, let us stop it here, we will discuss in the next class.